So this video is going to start from where we talked about previously for finding the electric field from discrete charges to build that up for distributions of charge or continuums of charge. So the first thing that we're going to do is we're going to revisit the superposition principle. Then we're going to talk about the infinitesimal electric field equation. Afterwards, we'll talk about dl, some tiny little bit of length for straight lines. And then we'll finish up talking about dl, that same kind of idea, tiny little bit of length for circular arcs. So starting with the superposition principle, we saw previously that if we had a single point charge that was a positive charge, and we wanted to find what the electric field was that it produced at some point represented here by this blue dot, then it's just going to be some line that's pointing directly away from it. Now, we could add an additional charge here, and then we would have another electric field line. And we could add another one, and another one, and another one. So now we're building up a continuum, and we can fill it up completely so that we really have a continuum here. And then replace that with, rather than having discrete charges, a bar of charge. And now when we're looking in this framework, what we can do is we can say that for this bar of charge, we have these tiny little bits of charge we're going to call dq. And each one of these dqs creates a tiny bit of electric field we call dE. Now, this entire continuum can be broken up in the same way. And then we can talk about all of the electric field lines that point from each one of those dqs to the point that we're interested in. And in adding all those up, essentially we're taking an integral. That's going to give us the total electric field from this bar. Now, looking at this equation in more detail, we want to actually quantitatively relate dE and dq. What we can say is that dE is going to be equal to 1 over 4 pi epsilon naught times dq divided by r squared times r hat. So effectively, this equation is almost exactly the same as the equation that we had for the point charge. Now we just have a dE instead of an E and a dq instead of q, where dE is going to be the tiny amount of electric field produced by each one of the dqs. We also have r, the distance from each one of those dqs to the point of observation, or where we're trying to measure or say what the electric field is, and the unit vector, r hat, that points from dq to that point of observation. Now, let's look at dq in a little bit more detail. And so when we're talking about adding up all these dqs, we can't just add them up ad hoc. We have to describe them geometrically. And so the way that we're going to do this is we're going to say that each one of these dqs can really be represented as some charge per length, some lambda, times some dl, where dl is some infinitesimal length. And so if you look at this in terms of dimensional analysis, we have charge on the left, we have charge per length times length on the right, so this is dimensionally correct. Now let's look in a little bit more detail how we can describe each one of these dLs for various situations. Along the x-axis, we have some charge that's spread. We would say that dl is going to be dx. If we had a charge spread over the y-axis, we would say that dl is dy. Now, the last thing that we can do is, rather than talking about this charge spread over a straight line, we can talk about circular arcs. So consider some xy coordinate system with some arc of charge that is along the arc of a circle of radius of r. And what I first want to do is talk about how we define arc length. So arc length, the arc along the arc of a circle, is given by the radius of the circle times the angle over which this arc extends. Now we can use this same idea to talk about some tiny little bit of length by saying that dl is going to be equal to r times d theta, where d theta is just a tiny little angle instead of the whole angle of theta. Now, something to be careful of here, when we're doing these kinds of problems where we have arcs of charge, the electric field is going to point from the arc of charge to the point of observation. In this case, if we were looking at finding what the electric field was at the origin, this tiny little amount dE from this dq that we have here would point to the origin like this. So you have to be careful with the way that you're defining your r hats. And that's going to be it.